Hello, my name is Steven Alvarado, and I'll be presenting our ECS 174 project based on 3D object detection for autonomous vehicles. The team members for this project are myself, Ankit Goel, and Elwin Dang. The autonomous vehicle industry continues to see rapid growth, ever increasing in popularity as we see a higher prevalence of these vehicles with autonomous driving on our roads. However, the promises and perils of such a novel technology means that safety is one of the number one priorities when it comes to the engineering of autonomous vehicles. As such, visual perception maintains a critical part of training such models. Our motivations for this project is to utilize visual perception data through fusing LiDAR and camera sensor detections. With this, we hope to simulate and identify real-world perception challenges in the realm of autonomous vehicles and the precision required to make this technology reliable and safe. For this project, we'll be using the Waymo Open Dataset, which is one of the largest datasets for autonomous driving. This dataset contains a plethora of LiDAR and camera sensor data for our purposes of detecting real-time 3D objects, such as vehicles, pedestrians, and cyclists. As an overview, there are two major parts to this project. The first part is object detection, where we utilize deep learning with a bird's eye view map, 3D point clouds, and performance evaluations to optimize our approach. The second part consists of object tracking, where an extended Kalman filter is used to track vehicles over time and is based on the LiDAR detections fused with camera detections. To go into more detail with this, let's look at our methodology. Step 1 is to compute 3D point clouds using the LiDAR range images. The OpenCV library is used to visualize the range and intensity channels, while the Open3D library is used to view these point cloud images on a 3D viewer. Step 2 is to create a bird's eye view map from the point cloud data, where we compute the intensity layer and the height channels to visualize the heat maps and height distribution of the surrounding vehicles. Finally, step 3 is where we extract our 3D bounding boxes that highlight pertinent objects around the vehicle, where we use a complex YOLO model for 3D object detection that compares the responses with the ground truth. As for our results, we use 3 performance metrics to help evaluate our experiments. The first metric is intersection over union, otherwise known as IOU. A detected object is labeled in the event that the IOU exceeds a certain threshold. The next 2 metrics are precision and recall, where we compute over the false positive values and the false negative values, which helps us gain valuable insight on the model's performance. The final metric is accuracy, which is a common measure that indicates how often the model makes correct predictions. To ensure the safety implications of our model in the context of autonomous driving, keeping these metrics high is crucial. The results of our performance measuring are shown to the right, showcasing the effectiveness of LiDAR-based detection. With that, this concludes the presentation for our ECS 174 group project. I hope you found this overview interesting. Thank you and have a good day.